Hey guys, this is Professor Janacek, and I want to go over an application for vector-valued functions. Let's take a look at motion. To begin, let's let the position of an object moving in three-dimensional space be given by the vector-valued function r of t, defined by f of t, g of t, and h of t for t greater than 0. The velocity, then, will denote as the vector v of t is given by the derivative of that position function r of t. The speed is the magnitude of velocity, and acceleration will denote as a of t, the vector, and that is the derivative of the velocity function, which is, of course, the second derivative of the position function. Let's take a look at some examples. Let's find the velocity, speed, and acceleration of r of t given by 1 minus t squared for the first component and 3 plus 2t cubed for the second component for t greater than or equal to 0. Now notice this is a vector given with only 2 components instead of 3 as above, but you've got this. It's the same idea. You should be able to get this no problem. So the velocity v of t is simply the derivative of the position. So simply take the derivative of that one, and let's see, what do we have? Oops. Negative 2t for the first component and 6t squared for the second component. Now the speed, it's the magnitude of that, which is the square root of the square of each of those components, the sum of the square of each of those components. Which gives us, let's see, that would be the square root of 4t squared plus 36t to the fourth. Oh, it looks like we could factor out 4. The square root of that is 2. We could also factor out a t squared. The square root of that would be the absolute value of t. And let's see, so that would leave us with 1 plus 9t squared inside the radical. All right, there we go. That is speed. Now for acceleration, a of t, we simply want the derivative of the velocity. So we'll take the derivative of those two components. So let's see, that gives us negative 2 for the first component and 12t for the second component. There you go. That's it for the first one. For the second example, we're going to find the velocity, speed, and acceleration for the position function 2e to the 2t plus 1, e to the 2t minus 1, and 2e raised to the 2t and minus 10, again for t greater than or equal to 0. All right, so the velocity, v, is the derivative. So we want to take the derivative of that position function. Remember how to take the derivative of exponential functions, and of course we'll have to use the chain rule, so take a little time with this if you need. Oops, according to the chain rule, we end up with, there we go, 4e to the 2t for the first component, 2e to the 2t for the second component, and 4e to the 2t for the third component. The magnitude of that will give us the speed. So let's see, the square root of 4e to the 2t squared plus 2e to the 2t squared plus 4e to the 2t squared, which is, what do we get? 16 and 16. Oh, I think put it all together, 16. We get 36 e to the 4t. And we can actually take the square root of all of that. That gives us 6e to the 2t. All right, there we go. Now the acceleration, left off, okay. Our acceleration, a of t, will be the derivative of our velocity. So let's see, if we take the derivative of those components, we end up with, again, using the chain rule, that gives us 8e to the 2t, 4e to the 2t, and then again 8e to the 2t. Not so bad. Now let's go the other direction. For example 3 here, let's find the velocity and position vectors if we're given the acceleration. So here we've got acceleration. Now, we also have initial velocity and initial position. So let's see. If we can go kind of backwards from this, the velocity function will be the integral of the acceleration with respect to t. All right, so let's see. If we want to integrate this vector with components 1 and 2, we end up with, for the first component, t plus some constant, I'll call it a1 for the first component. The second component will be 2t plus some constant, I'll call it a2. Now, if we're looking at our initial velocity, 1, 1, we know that our t value is 0. And so that gives us 0 plus a1, again I'm looking at this component, is equal to our first component 1. So a plus a1 is equal to 1. And then again I'll take the second component, t is 0, and that's going to be equal to our second component here. So we get 2 times 0 plus a2 is equal to 1. And so from both of those we have, let's see, that if we solve those, a1 is then 1 and a2 is also 1. So we can go back and use this in our original vector function, just replace those values, and we have v of t is equal to t plus 1 and 2t plus 1 for the second component. All right, there's the vector. There's the velocity vector. Now we need the position vector. So our position vector r is equal to the integral of the velocity. So that will be and we will integrate t plus 1 and 2t plus 1. Which gives us 1/2 t squared plus t plus a constant, I'll call it b, 1 for the first component. And then on the second one, we end up with, let's see, again, we're integrating, not differentiating. So that's t squared plus t plus a constant, which I'll call b2 for the second one. Of course, in our initial position, we have the components 2 and 3. And again, this tells us that when t is 0, we get those two components. So using the fact that t is 0 in here, we know that that's going to be equal to 2. So we can set up the equation that 1/2 times 0 squared plus 0 plus b1 is equal to 2. And for the second one, take this second one, t is equal to 0, set it equal to 3. So that gives us 0 squared plus 0 plus b2 is equal to 3. Solving those last two little equations there, solving this guy and this guy, we get that b1 is equal to 2 and b2 is equal to 3. So now we can write our position function r of t. Again, I'm going to just basically rewrite, so you can see it. This one, there's our position function, but now I can replace those constants b1 and b2 with their values. So that gives us 1/2 t squared plus t plus 2 for the first component, and t squared plus t plus 3. Let's make sure that's legible. Plus t plus 3 for the second component. And there you go. Enjoy.